Good morning, everybody. So, today I want to talk about membranes and get more into the mathematical aspects of dealing with membranes. I actually ended up spending a good bit of time preparing the notes, but I don't feel like it quite shows because I sort of ran out of time at the end, and there's some I'm going to have to do by hand for the last slide. And then this morning I realized I wanted to add a few things here at the front, actually just now. So might be a little more scattered than I want, but ultimately what I want to do is talk about the factors that influence our concepts of how much flux we're getting out of a membrane, what kind of pressure we need to apply, and how to model those mathematically. So this slide and the next couple are kind of basic. I'm taking from notes from my undergraduate class so that we can have more of a baseline, simplified view, and then we're going to go a little deeper, and then you start using our book's nomenclature. I'm saying that in hopes that we can avoid some confusion. I think the nomenclature is actually fairly similar. This uppercase R, we'll see a different one that's a little more artsy looking. It's kind of like a cursive R, like that sort of. That'll be our membrane resistance, but right now we're just talking about this fraction rejected. So a couple little things like that, but kind of big picture here, and I'll put the I did post most of these slides to Moodle if you're following there, except for these first three, which I just added. So I'll put all of them on Moodle when we're done here. Okay, so for taking a look at the membranes, last time we did a very simple example problem at the end, just to start thinking about, okay, we have a membrane that's rejecting stuff. How do we do this mass balance? And as you saw, in a simple case, it's just basically a word problem, right? It's something that you could do without any knowledge about membranes, just knowing that some stuff was removed and your volume changed. So to describe a little more precisely that type of concept, we can describe the fraction rejected as 1 minus the fraction remaining in the permeate after we pass it through the membrane, right? So if we compare the concentration in the permeate here to the concentration that we're feeding to the membrane, that's the concentration that's remaining in the cleaned water. So 1 minus that's going to be the fraction of stuff that we rejected. Okay, and we kind of looked at that with that problem last time. So that's fairly straightforward, introducing these concepts that we have that concentration in the different flows. We can take the log of that and call that our log. So that's a log-based rejection. And so if we describe a system where we have 99.99% of these algae cells removed, for example, then that's going to give us an R log of 4, because that 0.9999, if you take 1 minus that and take the log of that, that's a log of 0.0001, 10 to the minus fourth equals that. So that's where we get that 4, because we take the so you can see pretty clear, pretty simply there. So sometimes that's worthwhile just to think about our units that way, because we've got systems where we reject quite a large fraction at sometimes, and we want to be able to just talk about it in a kind of a convenient manner. We can also take a look at simply the water balance basis of kind of on the net scale, how much water are we recovering? If we're, let's say, desalinating and we want to know how much of this water is actually recovered compared to wasted as brine, right? So we would use this little lowercase r as the water recovery rate And we can think of that as the comparison of the flow rate in our permeate, that treated water, compared to the feed. So for something where we just have a very simple system that's doing just a very basic filtration, maybe our recovery is near 100%. Almost all the water is saved and used, and just a little bit of it is going off. For something like desalination, maybe it's only 40% recovery, something like that. So it all kind of depends on the situation, the context, how much fouling we're getting, and how we need to operate the membranes. Okay, so as an example, we could describe these cubic meters per second or whatever. And of course, our total flow is going to be our feed flow. And so we can split that into what's rejected or in our retentate and what's in the permeate. So if we had 100 liters per minute of water, 15% of it goes to waste, then our R is going to be 85, or 0.85 for 85%. So pretty simple there. Just wanted to kind of touch on those. And the last one here, we'll say a flux. Anytime we're talking about flux, this is going to be essentially looking at the transportation of water across our membrane. So if we have some membrane with a known surface area, the flux is really talking about, it's essentially a velocity term going through the membrane, but it accounts for the surface area. It's like a flow accounting for the surface area, or just simply a velocity term through. So the flux then is the water going through, and we could describe that as meters per second, or perhaps more accurately, something like cubic meters per square meter per second, or hour, or whatever. So that's the concept here. We see flux in a lot of different cases, but when we see J, that's going to typically be our flux. Here I had the units written already in liters per square meter per hour. And if you were to convert that to cubic meters to liters, then you'd see that can simplify to meters per second, or meters per hour, or whatever. So essentially that's going to be that Q permeate, so the flow that's making it through the membrane, divided by the surface area of the membrane. So we could think about it and say, well, is it the Q feed over the area? I would say that's not correct, because that's not actually passing through, right? It's the membrane is receiving that amount of flow, but some of it's just passing along. We do need to do this on the basis of the permeate in order for that to make sense. Okay, and AM here is the surface area of the membrane. Okay, so with that as sort of the bigger picture concepts that I wanted to review with you briefly. And with that, I want to get into some more of the technical stuff that our book deals with, and start off talking about the way they're using the nomenclature. So when we look up one of the equations, or we take a look, we can have some idea of what exactly they're talking about in the context of some membrane system, or more often probably just at an individual membrane level. If we're talking about having a membrane here and doing some sort of a description, what are we talking about? So like we've said before, we have C would be our concentrate. So if we've got a membrane feeding in here, and then a rejected stream there, our concentrate, and then a permeate coming here. So this would be our permeate, this would be our concentrate, and this, of course, is our membrane. So when we're describing a membrane and describing this process, we could potentially look at a different view where we have a membrane, water's coming in, some is going out, and some is going through, right? So then it would be M here, C here, and P here. So we could kind of look at that as C is here, right? So the concentrate side of the membrane is where the foulants and the rejected stuff is starting to accumulate. So either way you want to look at it, we've got these three descriptors, and so we're going to use these to describe where something is being measured or where something is happening as we go. So then kind of one of the questions will be, we're looking at the pressure drop across a membrane, but which components are we specifically talking about? And we'll notice that we'll have like delta P, but with some subscripts here to say maybe at the membrane surface, or the pressure drop across the membrane here. And sometimes we'll also have a secondary description that we're going to get into and describe exactly what we're talking about here and why we care about that. So if we just have one subscript for this delta, then what we're talking about is we're referring to the bulk solution in the given location. So if we were to say the delta MP here, what we're talking about is the membrane, we're doing the pressure drop across the membrane, and then in the bulk solution on either side of the membrane. If we do have a subscript there, so like this delta M C/P, all that for the pressure drop here. So it's like, this is meaning we're talking about the pressure drop. This is some difference, that differential here, or describing as a drop. That's then what we're looking at is we're looking at it at the interface of the concentrate and the permeate. So maybe this is not the best drawing here, but we're measuring it for this membrane like right here and right here. So it's measured really right there at that interface. So immediately across it, right? So then that would be different than having a pressure gauge measuring in solution here or here. Okay, so then we can use this for not just the pressure, but we can use this for other things like the concentration. So if we have some species I that we're interested in, so C sub I, so concentration of species I at the membrane, then what we're really, this next subscript is looking at the interface between the membrane and the permeate. So rather than measuring just across here, what we would be doing is looking at between the membrane and the permeate. That would be kind of on this interface here, on that side of it. So maybe a little small to tell here, but that's what they're referring to. And a lot of times once we derive an equation that's generalized and for practical purposes, most of this stuff kind of goes away. But in the process to get there, maybe looking at different assumptions, we need to say, okay, well, we are going to assume that the concentration here is the same as in the bulk, or something like that. You can see as we get into it, there are some times where we see that it could matter, and so we need to make some assumption because we can't actually measure the pressure inside the membrane. It's just not practical, so we have to take some things with a grain of salt, or make some assumptions to be able to work with it practically. So these descriptors are what the book is using to describe exactly what's going on and exactly what they're talking about. Okay, so this is that concentration as measured at that interface of the membrane and the permeate there. Okay, so just a couple more examples. If we had delta M sub M for the pressure, that would be the pressure difference across the membrane with both pressures measured inside the membrane. So if we had, I'm going to draw a larger membrane here. If this is our membrane, and maybe we have kind of the separation layer here, and then more of a supporting structure here with larger pores and everything, then maybe we're interested in measuring that pressure difference across the membrane, and somehow what we would need here to describe exactly this guy is a pressure gauge here and a pressure gauge here inside the membrane, measuring that difference from one side to the other. That's my understanding of what it's talking about. So again, that in particular is not practical. So instead of doing that, for practical purposes, we describe the transmembrane pressure, which is kind of our driving force pushing stuff across the membrane, as delta Cp, or C/P. So the pressure difference as measured, or at the interface of, instead of these two, so this would be here, then this guy is looking at pressure gauge here. Well, and there's only one subscript, right? So this is actually talking about the bulk solution, not even at the interface. It's out in the bulk solution on either side. So actually, I'll use the other diagram for that. So this one would be measured with pressure gauges here and here, which is a lot easier to do because you can put those in line in the pipe leading up to it and leading out of it, things like that. So that's, ideally we might try to measure right here. Maybe there's some other factors that are going to affect the pressure, but this is the transmembrane pressure more realistically would look like that. Okay, so then we have some description of the pressure. Now, kind of the next step would be to understand, okay, how does that relate to a flux? So we can take a look at what's called a specific flux or a permeance that's going to describe, given some membrane and some pressure unit applied, what kind of flux do we get? And that's going to vary by the membrane, so we want to rate our membranes based on the specific flux they can provide. So our permeance or specific flux here is the flux per unit pressure difference between two solutions adjacent to the membrane. So just our flux per transmembrane pressure unit, okay? And this is something that we would identify as different from one membrane to the next. We've got a couple of images from our book here, kind of showing some pores in membranes. I'm not sure, this might actually be the same one, just with a cross section versus an kind of aerial view image. But if you take a look at different membranes, and I'll have a few other pictures, you'll see that in a lot of places there are quite a few differences, and you can see that there should be a difference in their permeance just by looking at them. It's like, yeah, there certainly would be more or less flux flowing through there. Okay, so then we can say this Kw for our specific flux, our permeance. We can describe that, and actually before we get there, one thing I'm going to say is this measurement of our transmembrane pressure I talked about. I kind of mentioned this already, but we can conceptualize that as our effective pressure difference, that effective pressure that's being applied and exerting our force for us. So as we describe this permeance, it's going to be this specific flux. It is the specific flux. It's going to be this flux, so J with a little hat under subscript V, and I think this is why I kind of ran out of time this time. Is all these little symbols. I finally realized in PowerPoint you can actually, I'll go ahead and show you. You can sorry. That was 16-year-old me. If you're editing an equation, oops, wrong one. there is a way to put the little hat thing there. This is the wrong PowerPoint. One second. No wonder I'm confused. So just in case you're interested, I realize there's different accents to add, and you can put in the little hat thing and stuff. So in case you cared. Things I learned yesterday. Okay, so anyway, we've got this J with a little hat, underscore V. That's essentially our flux that we're talking about right there. We take that, divide it by our, the per unit pressure differential across, adjacent to the membrane, between the two solutions adjacent to the membrane. So that's going to be our delta P effective that we have from C to P. In an ideal case, we can rewrite or rephrase that denominator as, or we can basically say all the equivalents. If it's an ideal membrane, if it's clean, the solution is clean, the membrane is clean or brand new or whatever, then all of these are equivalent down here. We can say that guy is equivalent to this pressure difference across the membrane measured within the membrane. It's also equivalent to that same thing measured at the interfaces of the membrane, and simply the same thing as the pressure. And here, instead of writing effective, we're just writing the pressure. So I think what we're saying here is that the measured and the effective are the same in the ideal case. So all this is just saying this is all kind of the same pressure as pressure in the ideal case. And so in the simplified form, maybe we just leave that as X for a moment, and we say that it's the flux over the pressure, or the flux divided by some X. And then we'll describe that ideal case, put a little asterisk here, and say this permeance in the ideal case is that flux over X, and then we can model this system based on what happens in a capillary. Okay, so if we think about these membranes as if they were essentially a network of small capillaries allowing water to go through them, something like that, then what we can do is take this permeance and say that what's going to happen here is effectively the same thing as what's happening as if we just had a pressure across a capillary in an ideal system. So water is just flowing through a capillary and out the other side, and that gives us, given these ideal conditions, that gives us a way to describe what happens in a membrane from a fundamental point of view. So, and when I say fundamental, I mean we don't actually have to go and observe what's happening there and build an empirical model. We can derive that model based on our knowledge of flow through pores, flow through capillaries, viscosity, these types of things. So that's what the book goes into and derives these equations here and starts describing this. This is called the HAGEN. I think that's not supposed to have an I there, I think. HAGEN and I don't know how to pronounce it. I think it's POISEUILLE or something equation. And essentially that gives us a roadmap to do the permeance or the specific flux calculations on that fundamental basis without doing the observation. So that's one thing we can use if we build a membrane and we have a good idea of what the effective capillaries are like. Then we could calculate this from that standpoint. So this is useful in a sense because if we have some idea of some of these different parameters, which I'll go over in a second, then maybe we can just simply measure those parameters, like how many pores surface area do we have? How big are those pores? Then we can use that as a way to understand our permeance and predict it for a given application or a given design. So there's value there, even if we could just do some observations and say, okay, well, we've applied this amount of pressure and we've got this flux. What's our result? This also means that if we can use this type of situation to say, well, if we are getting some sort of fouling and we're noticing that's affecting our permeance in some way, or our flux and pressure requirements, then maybe we can better understand the fouling process itself, given that our baseline assumption when it was close to ideal was this is kind of flow through capillaries. So how did the fouling change that? Maybe we can use that to better understand what's happening here. So that equation, just rewritten up here, there's a few pieces of it, just wanted to point out. So we've got this, I guess, eta M, that's the membrane porosity. It's probably the wrong term. Is that eta? You guys remember? This guy? I never remembered. Epsilon?
Is it epsilon?
I don't know. Something. Whatever. That one. That one is membrane porosity. I always feel like I should know these, and I'm like, Okay. So, and that would be the ratio of pore area to membrane surface area. So, kind of makes sense, right? We see all these different pores, and we map or we calculate what area is occupied by pores to the total area that we've defined. That's going to be that membrane porosity value. This one, which I did just look up earlier and then I forgot, I think they essentially just took a look at the Greek alphabet and figured out which one most closely resembles the word tortuosity, and just picked that one. I think that's what happened here. So that one's the tortuosity factor. That's essentially describing, when you're in the pore, how many movements, how many directional changes, how tortuous is that path before it goes from the surface through. And this particular example looks like it's got a relatively low tortuosity factor because the way that one is fabricated looks quite straight lines, straight pores there. But that's going to change depending on your membrane material. And it's in some sense, maybe you have some types of materials are better optimized, but there's lots of pros and cons for any given material. So it's certainly not the only factor that would matter, but it is something that plays a role in deriving this flux here through a capillary, right? And that's why in the previous stuff we were deriving this permeance so that we could describe that flux divided by some pressure, and we just kind of left it at X because I think the book was just making the point that we're going to focus on the flux aspect, and in the ideal case that pressure is just there, so we'll add it as needed. So from here, this discussion is really focusing on that flux through a capillary, so we can understand what impacts that. Okay, so then this next one. Is this sigma? Which one is this? That's sigma? I think, yeah. Okay, so sigma m, that would be the membrane thickness. So what we're looking at is all these different parameters that's going to affect how that flux is changed, and of course the thickness of the membrane itself is going to be important there. Then finally we have this relationship, the number of pores divided by the area of the membrane, so n pores divided by AM. So we see that here, and the mu is the dynamic viscosity of water. So if we take a look at this equation up here, really three different forms. We've got that number of pores per area. We've got some function of the pore radius to the 4th power times pi. We've got a pressure difference across the membrane as measured at the interface between the concentrate and the permeate. All of that divided by 8 times the viscosity times the tortuosity times the thickness down there. And so that gives us a definition of the flux given some pressure applied here. What flux do we expect given all these aspects of these pores acting like capillaries in a membrane? Okay. So we can potentially use that given, again, the kind of ideal solution, ideal system assumptions. We could then use that. That's not to say we can't use the stuff we mentioned earlier. I think let me backtrack real quick. The flux more simply. Well, I guess we just simply defined it here. We could also, well, we'll get to it, but we can define flux also as kind of a very rudimentary way with just looking at the transmembrane pressure divided by resistance, I think. Okay, so at any rate, okay, we talked about this one. So I want to just give a few more visuals about those aspects that we were talking about, right? So we have, if it's acting like capillaries, we can imagine and observe here the tortuosity factors here, not so bad, a little bit of curvature sometimes, a little bit more so in this case, and this case. And you can see how that would be variable. If you have a material that's more accurately, or if this image over here is kind of showing the pore itself in the membrane is acting like that, but then maybe you add some fouling of particles on top of that, and then you get a system where your effective membrane is tortuosity like that, and water has to travel through some condition like that. So the fouling layer turns out to play a big role in these impacts as well once you have that fouling taking place.
How would you measure tortuosity? Like how is it like a fraction or is it like a number?
That's a good question.
Factor.
I think it's a factor. Yeah. So it's a factor, and I think it would be.
It's just a very odd thing. Like I don't know how you could possibly like quantify it. Like, oh, it's been this many times. It's like I
Right.
No, it's just very odd.
No, it's a good question. And maybe we'll take a look at the book in a few minutes, see if they talk about it more. I would guess that it's some, since it's a factor, you multiply, here where it's applied to essentially the thickness and the viscosity. So I would guess that the way it's applied is like, all right, well, if it was exactly a straight thing, then our distance of the capillary would be pretty well known, right? That it's just going to be a cylinder X distance long. Now, if in effect, if that assumption is not working, but everything else we have control over, but it's like, oh, the length is effectively doubled, then I think this tortuosity factor might be 2, because it like kind of took a bend and then came back and it doubled the distance that it has to travel. That'd be my guess is the way it works, or along those lines. Okay, so yeah, just a few examples here. This one, right, here's a pretty neat example because you can really clearly see the very fine separation layer here where the pores are practically invisible, and then a thicker, much more porous, much you can tell the permeance in this supporting layer is going to be a lot better. Now, I might be wrong, and this might actually be the membrane itself and then a fouling layer on top of it. I guess that's possible, but from the looks of it, I would guess that this is a support layer, and then that's the separation layer. Maybe this is the separation layer, and then that's the fouling, but I think that technically this is all support, and then separation right there. And you can kind of see the same thing in this one where it gets a lot more fine right up in here. That should be our separation layer, and below that is the support. But at any rate, you can kind of see and get a feel for this. These factors are all going to be really taking part here, and each going to be important in their own way. Okay, so membrane resistance then, and here's one place where we can relate the flux I was talking about. So membrane resistance, you might think of different things when you think of resistance, different physics, different aspects, different definitions of the word. Here, the best analogy is really going to be the electrical resistance, where you have in the electrical world, your resistance is equal to some voltage applied divided by the current you get. And so here with the membranes, and that's would be essentially the flux of electrons across a resistor, where the voltage is analogous to our pressure, right? So that's some driving force. So the voltage, this would be like delta P. Current, this would be like J, and our resistance in both cases would be the resistance, right? And for this, it would be the resistance of the resistor versus the resistance of the membrane. So with that, what we can say is really our resistance, we can define it as that pressure required to drive a given flux. So we can define it with a little r with the 2 bars above it. The book says that's our resistance at a specific region, and that's just going to be the delta P effective divided by the flux. Now, for resistance in general of the membrane, we're going to describe it the same way, but we're adding the dynamic viscosity of water there. So this is our more general equation that it's going to be applied to the membrane as a whole. So this is going to be quite useful, and what we can see is we can also rewrite this if we wanted to. And I mentioned that TMP as our transmembrane pressure. We could rewrite this and say that's, in general, that's equal to transmembrane pressure. And so then we could describe our system. If we wanted to know our flux, we could describe that as our transmembrane pressure divided by mu times the resistance. Say that. And maybe we could solve for the transmembrane pressure as well, alternately. So we can manipulate that and solve as we see fit. And we can also recognize here that all of those things that we were talking about a moment ago, with all those different parameters going into deriving what is this flux, those all can also be placed into here, and then we have a very complicated expression of the membrane resistance for that system, and we can pretty much define the resistance nearly completely by those physical aspects that we may be able to measure or somehow know about the membrane. So what we're seeing here is a kind of a dichotomy between looking in practice and just physically observing what's happening, and then building up to that given some known aspects about how big the pores are and how thick the membrane is, things like that. Okay, so one last discussion point here would be membrane permeability. So we talked about kind of a permeance or specific flux and the resistance. Now permeability is a lot more like what we'd call porosity if we're dealing with flow through porous media. Flow through sand grains and stuff. And here's where it just, I guess, was taking me a lot of time to put all the equations in nicely, so I'm just going to have to do some of this by hand at this point. But so our permeance here, or excuse me, our permeability, if we think about those images we were taking a look at, certainly some of them look quite permeable compared to others, right? So, you know, if you have a bunch of fouling on it, that looks like it's reducing the permeability, and sometimes you could even consider fouling does block inside the pores sometimes. So there's a, I think we'll spend a little more time talking about fouling next time, and how to understand it, things of that nature. But here we'd call that a cake layer that's forming a cake on top, and then we're doing cake filtration, where that fouling layer is really acting like our filter at some point. And you can see, you know, the different porosities essentially in here is the point. Okay, so we can define a permeability coefficient, K underscore V. This is going to be in length cubed. Our units are going to be length cubed times time divided by mass. And then we can describe an intrinsic permeability, KV intrinsic, and that the units for that one are going to be length squared. So both of these are going to be important, and we can relate and say that our KV intrinsic parameter, that intrinsic permeability, is equivalent to the resistance of the membrane divided by the thickness of the membrane, the inverse of that. So I don't know why we didn't just write that, you know, the thickness divided by the resistance, but that's how the book said it, so I'm just left it that way. But that should be the same thing, right? I don't know what their reason was. I'm supposing they have one. But so that's the equivalence there is essentially the ratio of thickness to resistance. Okay, so that gives us right up front kind of a sort of a straightforward grasp of what they're talking about. Another way to, one thing we can do is say this is equal to our dynamic viscosity times the flux divided by the pressure drop at the membrane surface, or excuse me, pressure drop as measured, you know, at the interface of the membrane, at the interface between concentration and permeate. Okay, right. So the first subscript, that's the location. The second is at an interface between X and Y, whereas concentration and permeate there. Okay, all of that divided by the thickness of the membrane. Okay, so essentially what we've done here is we incorporated that resistance term. I believe all of this here is that membrane resistance, and we still have the thickness there at the bottom. Okay, so that's another way we can write that. We can also say that our permeability coefficient, Kv, is equivalent to that, the flux divided by the pressure difference, you know, essentially the same setup here without the viscosity term. Cp, or pressure, divided by the thickness. And then we can say that essentially this intrinsic permeability coefficient is equal to, or excuse me, the permeability coefficient is equal to intrinsic permeability, KV, intrinsic, divided by mu. And so that's what, essentially, if we look at the units for mu is kilograms per meter per second. So when we go from this permeability coefficient up here, if we divide that by mu, then we'll end up with length squared. So that's, we kind of could have seen that coming from just the units if we had thought about it up there. So really, essentially what we're saying is the permeability coefficient is the intrinsic permeability of the membrane divided by the viscosity of water. So that's going to depend on temperature, right? So here's, and I think that's why it sometimes makes sense to separate these out, because you might describe the permeability coefficient of a membrane, but then once you're actually applying some water that has a given temperature to it, then its intrinsic permeability changes. I think that's the way this is working. Actually, there was a master's student in the lab group I worked in when I was a graduate student, who was working with ceramic membranes, and since one of the advantages of ceramic is they don't melt if you heat them up quite hot, they're much more temperature resistant. And so he was working on a project where he'd use actually quite hot water for like coal-fired flue gas, or let's say coal-fired power plants using water to capture some of the contaminants in flue gas, then sending that through a filtration, and there's like free energy there. So if you use a normal filter, you have to let that cool, pass it through the cooling tower or whatever first perhaps, or use some other cooling line. But what they were thinking is like, well, maybe we can get a lot better permeability with the extra heat because the viscosity is lower, and make use of the ceramic membranes to actually derive a pretty good benefit, less pressure required to get the same treatment, given that we can handle that hotter temperature, and the temperature's there anyway. So that was kind of a neat use case for adjusting the things like the permeability and the other aspects that are influenced by the viscosity, where it actually made sense. Kind of niche, but I think the project was in some way successful. I think it was at least some good data came out of it. I know there was a publication or two. I don't know if the power plants that they were collaborating with are pursuing it or not, but I thought that was a neat potential application. Okay, so with all of that, just a couple things further here. So this flux JV, we can now define this in terms of this permeability, this intrinsic permeability of a membrane, and we can say this is going to be equal to the pressure difference across the membrane at the interface of C and P divided by the thickness of the membrane divided by mu times this intrinsic permeability. So a simpler way to write that would be to use the permeability coefficient and have this transmembrane pressure divided by the thickness of the membrane. Okay, so that gives us a flux given the permeability, transmembrane pressure, and thickness, as opposed to using the resistance type stuff, right? So this is a different way to look at the flux, and we essentially accounted for the mu by putting it in this terms. Okay, so that's that's potentially useful, and it turns out this is actually fairly similar to Darcy's law for flow through porous media. Just kind of as a caveat or a side note there. Okay. The other thing we can do is relate this back to the HAGEN-POISEUILLE equation. And we can take a look at the equations that the book provides here, and say, okay, well, this intrinsic permeability, we can define it then, because we had that relationship here with the flux, we can then relate the intrinsic permeability to the capillary action that we were talking about earlier in the lecture. So that's what they're doing here. They make this equivalence where that intrinsic permeability is equal to the area of the pore times the radius of the pore squared divided by 8 times the area of the membrane times the tortuosity. Okay, so they end up having that, and also a relationship with the resistance that is kind of similar, you know, that inversion where we had this guy. I think that's coming to play where they solved for the resistance of the membrane there from that equation and got this part. So, and here the book, again, I was trying to get the notes and get them down more quickly so we could discuss them. And so the book describing these at the end of this section was saying, so note that by comparing a couple previous equations, which I think I just flipped to those, with another, we see that this HAGEN-POISEUILLE equation provides a theoretical approach to predicting this intrinsic permeability and the membrane resistance of a porous membrane from purely geometric considerations. That's kind of what I was meaning. That's the word I was trying to find earlier when I was saying from this fundamental standpoint, knowing something about the geometry there. And that's as long as the flow through the pores is fully developed and laminar. So again, kind of an ideal situation. We can describe the membranes and their key factors in terms of this permeance, the resistance, the permeability then, all based on the geometry of what's happening inside them. So hopefully my goal today was to show that and condense it enough so that it was, you know, that sometimes I feel like the book's just like trying to brag and show off with their equations. I mean, that's just maybe just me being, you know, annoyed at the book. But hopefully we've been able to take a look at those and say, okay, well, here's this meaning, and then we can take a step back and say, okay, well, that means we can hopefully apply them in some system, making some assumptions, and make some sense of that. Now, obviously, there's a lot to go into, especially in the case where you do have fouling or some non-ideal conditions, and the book is actually really great. I think if I were to ever have to go and solve a problem here in the real world, I would really like to have this book, I think, so that I could actually take that deep dive and figure it out. But you know, just trying to teach you the principles here, anyway. Okay, so example 15.3, I think we've got a little time to work through this. So let's take a look and see what we can do on it. So a symmetric membrane has a thickness of 75 micrometers, pores with a nominal size of 0.04 micrometers, and a tortuosity of 1.5. So there's an example of that tortuosity factor, right? So maybe I think that means it's extending those pores effectively by 1.5 times the vertical length. And a ratio of pore area to membrane area of 0.06. Assuming that flow can be treated as Poiseuille flow, predict A, the intrinsic permeability, B, the membrane resistance, C, the flux through the membrane, if it is used in a system that is fed pure water at 25 degrees Celsius, and it gives us our mu there, and the transmembrane pressure is 20 kilopascals. Okay. Also says, note that because the test fluid is pure water, all the pressure drop between the concentrate and permeate occurs inside the membrane. So that's a note that kind of helps explain why we were talking and caring so much about all this notations, because if it was not clean, then you would start having a pressure drop before the membrane potentially with the fouling layer. So that's where this kind of stuff ends up becoming important. So you'll definitely need some of the previous equations. I'll try to work on getting them up here for you to work with in a moment. Part D, I'm just going to finish reading this and then we'll let you get to it. Flow rate through the membrane. Predict the flow rate through the membrane if it is used in a laboratory scale apparatus that holds circular membrane discs with a diameter of 6.5 centimeters, and the system is operated as described in Part C. Okay, so go ahead and start thinking about that. I'm going to write up a few equations here, and then we'll see what we can work through in the next 15 minutes. well, let me work through a couple of these with you here and get you the answers. The book, of course, has the solutions on the same page, but we'll talk about it real quick in case you have any questions or anything that we can work through together here. So for A, the intrinsic permeability of the membrane, we're essentially given the dimensions, so it would be a matter of applying this equation, making sure our units are consistent. I think it's probably best to work with meters directly in pretty much all cases, in case there's, I mean, maybe this one it wouldn't matter, but most of them will be dealing with mu, and even our pressure units are going to relate to meters when we're, pascals I think are in terms of newtons, which are in terms of meters. So basically we want to make sure we're converting appropriately in almost every case. So in this case we could write this using our equation up here as, cursor would show up again. I don't know why my cursor disappears sometimes, but it's not very helpful. Okay, so 0.6 times 4 times 10 to the minus 8 meters, all that squared, divided by 8 times 1.5. And that should give us a value for the intrinsic permeability of a very small number, 8 times 10 to the minus 17th. And this is going to be in meters squared. Okay, so it didn't matter that we converted to meters because that's the, well, I guess length squared units are the intrinsic permeability, but we'd want it in meters anyway at some point. Okay, so that would be part A. Part B, we're looking for our resistance, so we can use our equation here for the resistance. This was a derivation essentially from equations 15 and 16, or excuse me, from this was equation 15-16 put here. So then we can write that out. So this is going to be 8 times 1 over 0.6 times 1.5 multiplied by 7.5 times 10 to the minus 5th meters divided by, again, that area of the pore, that radius of the pore squared, right? Or the 4 times 10 to the minus 8th meters squared. Yeah.
That nominal pore size, is that the radius or is that just I thought it was the diameter.
Okay, yeah, that's a very good question. Apparently the book's treating it like the radius. That's because I'm just had the solutions from when I took notes from the book. So yeah, I would think that normally I would normally think that would be the diameter. So, but this apparently is treating it like the radius. So yeah, it's interesting because normally when we deal with particles, we assume it's, the nominal particle size. We assume that's the diameter. So I'm not sure why exactly, but I suppose that's in this case that's the radius.
Why don't they just say radius?
Or I mean, sorry, what's that?
Why don't they just say radius? Why are they confused?
I don't know. So if you do it, and if you do it the other way, the answer will be different, but probably not hugely different. Factor of 2 maybe or something, or maybe 4. But solving it this way, we get our resistance. It's supposed to be the fancy R. Would be 9.38 times 10, oops, times 10 to the 11th per meter. This is it's typical for the membrane resistance to be very high like that. And if you think about it, you can kind of envision, okay, if you had 1 meter worth of membrane, that resistance should be a very large number, whatever resistance means. You know, it's a very small amount of stuff or a very high amount of pressure to push it through 1 meter, right? And the units of resistance here are per meters or per distance. So in that way, it kind of feels right that it's a very large number per meter. Okay, so that was the answer the solution gave for that. For the flux here in part C, one thing to note here is we need to convert from kilopascals, so 20 kPa is going to be equal to 20,000 newtons per square meter. So 20,000 pascals. This is also the same thing as writing 2 times 10 to the 4, and we can write newtons as kilograms per meters second squared. Well, kilograms meters, so that meter cancels there, but that's a one way to simplify it in terms so that we can get it into newtons and meters. And then the other thing we need to do is it asked us to report in liters and hours, so that's one of the reasons why we needed to isolate seconds and meters so that we can eventually convert back to liters from cubic meters and hours from seconds. So once we did this, we can plug in and then do the conversion. We're pretty much out of time, and I didn't write it down anyway last time, so we're gonna assume we did all that. We can get the answer 76.6 liters per square meter per hour. Okay, so that the issue there would be to do those conversions first. Let's see. Okay, and part D was kind of just a follow-up there. The flow rate, and I didn't give you any equations here because I was hoping you'd kind of remember that our flow rate is going to be related to flux simply by the fact that a flux is a flow through some area. And so if we multiply that flux, which is flow divided by area, we multiply that by area, we end up with flow, right? So all we need to do here is take that flux times the area of the membrane, and that'll give us our flow, or our flow rate.
So you just get the area of the circular membrane does.
Yep. Yep. And so then we take that area, and we have the J now, and so we can just say simply J membrane times the area of that membrane disk. So we'll say pi, well, write it this way, pi times r squared, or in this case we'll do diameter of the membrane squared divided by 4. And all of that, once we do that, should give us 4.24, and then we had to convert to milliliters per minute, apparently, was the final answer. I don't know if they asked for milliliters per minute. I guess they didn't, but you could get it in liters per hour. That was 0.254. Or convert it to milliliters per minute or whatever. So, yeah.
So like, let's say you're trying to measure like your fouling, how much fouling you're getting. Like, would you compare your real observed flow rate to like theoretical or like your initial?
Yeah, that's an excellent question. So if we want to determine fouling, how are we doing that? It actually depends a little bit on the way you're operating the membrane. If you're keeping a constant pressure applied to it, then yeah, you can look at how your flux changes over time, and you'll notice your flux starts decreasing over time, and that'll be directly proportional to or directly related to the resistance increasing. And the way that the resistance increases will depend on what type of fouling. Like if it's just the cake layer, it does a certain way. If it's like including all the pores inside and clogging those, we'll get into it a little more. And I've actually worked next to lots of membrane experts. My PhD advisor had some students working on membranes. That wasn't me. My postdoc advisor was a membranes guy, except I was just doing photocatalyst stuff involved with that. So it was like, I've been around it a lot, and so I've seen my peers give presentations on like, oh, look at this graph that has unitless dimensions over here and dimensions of garbled million things squared and then divided by other irrational numbers or something. I don't remember what. And then it's like, you see this profile, and that means that that's associated with fouling inside the pores instead of just fouling on the surface. And right. So there's different ways to relate it. So you can do the flux if you're keeping the pressure constant, or you can monitor the pressure increasing if you're keeping the flux constant. It's harder to do constant flux, but you can do it with flow meters and stuff. So constant flux is what is typically done in practice because we want a certain amount. So there's practical reasons we do that. In the lab, it's usually easier to provide a very precise constant pressure and then see what's happening. And a lot of times what you're doing is just simply weighing the amount of water that's coming out, and over time, and you just have it on a scale, and then that's giving a digital feed to your computer, and it's like, tracking exactly what's happening that way. Okay, so that's it for today. Sorry again, kept you late, but we'll see you guys next time.